Hey everyone, this is Abhinav. Welcome back to our series on virtual memory. This is the fifth video in the series, and so far we have talked about the idea that the address space of a process uh, consists of virtual addresses, and the operating system maintains a mapping of those virtual addresses to physical addresses uh, in the form of a page table. So it maps one page of the virtual memory to one physical frame. And one page is usually 4 kilobytes and it is mapped to a 4 kilobyte physical frame. So whenever we try to do any memory access, the hardware uses the page table to translate that virtual memory address into a physical frame address, and then it looks up the exact data within that physical frame. It does this with the help of a page table walk, which is what we learned in the previous video. This video is a logical continuation of the same topic because just looking up the page table and translating a virtual address to a physical frame address is not sufficient for the hardware to do a proper memory access. It also needs to find other information about the page before doing the access. For example, the hardware, while it is doing the page table walk, it has to ensure that the page table mapping, whether that is a valid mapping or not. Because if it is an invalid mapping, then it should not be using that translation to access physical memory. So this can happen in the cases, for example, when the operating system uh, may performs a page reclamation. So whenever there is memory pressure, the operating system has to reclaim some of the physical pages and reuse them for other uh, processes. In those cases, it has to move those pages to the disk. So, for example, if those are anonymous memory pages, so allocated using malloc or mmap as anonymous memory, then it has to write those pages to the swap and then reclaim them for another process. Or if those are file back pages, then it may have to write those pages back to the file and then reuse those physical pages for other purposes. So in those cases, the page table mapping becomes invalid. So the hardware has to know whether those mappings that it is looking up are those valid or not. Uh, Apart from that, there are other things the hardware may want to know. So, for example, if you're trying to write to a page, it has to know whether the page has write access enabled on it or not, or whether it is a read-only page. So that information has to be available to the hardware. Similarly, when you're trying to execute a page, so if a page contains code and you're trying to execute it, so it should have the execution enabled on it, or it should be marked as a code page. So that has to be there. So all this information was also stored in the page table, and the hardware, apart from looking up at the translation, so apart from looking up the physical frame address, it also looks up all this metadata in order to answer all these questions to ensure that the access is valid. This is obviously required for safe and security of the system. Uh, so let's talk about. So in this video, we are going to talk about all this. What are all these flags and metadata that is stored in the page table, and how exactly is it stored? So how the hardware is able to find it. So let's start by talking about all the flags that are present. So all the metadata itself, and then we'll talk about how is it stored in the page table. So let's talk about all the bits. So one of the most important flags that is present in each page table mapping is the present bit. So it's called the present bit itself. Sorry. So the present bit is essentially telling the hardware whether the mapping is valid or not. So whether the mapping is present or not. So when the hardware is trying to translate one virtual address, it does a page table walk and it reaches a certain level. Then it has to make sure whether the mapping, whatever it is looking at, whether that's a valid mapping. So is the mapping itself present or not? So if the present bit is set, that means the mapping is present and it is a valid mapping. If the present bit is unset, that means either the mapping was never made. For example, when you allocate a new page, the uh, For example, when you're doing malloc, the operating system may allocate a new virtual page to the process, but it may not have mapped that virtual page to a physical frame yet. So the present bit would not be set on those pages. So that could be one case where the present bit is not set. Another example is the operating system has swapped those pages to the disk. So in under memory pressure. So when doing page reclamation. So again, in those cases, the present bit will be unset, which means whenever the process operating system reclaims those pages, it goes and unsets the present bit so that the hardware does not accidentally uses those mappings. So that is another example. Uh, so that is the use of the present bit. So it tells the hardware whether the mapping is valid or not, or the mapping is present or not. So if the mapping is not present, so when the hardware does a is trying to translate, it does a page table walk and it finds that okay, the present bit is not set. So what does happen? What happens? So the hardware raises a page fault. A page fault is sort of an exception that the operating system has to handle. So when the page fault is raised, then the kernel comes into the picture. So the kernel gets uh, executed. So kernel has to handle the page fault. So the kernel then goes and sees which uh, page you were trying to access and what was the reason why its mapping was missing. So the kernel would maintain that information in the processes uh, data structure. So whatever data structure it uses to maintain the virtual memory, it would store information about such pages. So for example, if a page has been swapped to the disk, then it would store in the uh, process processes data structure whether that page is swapped to the disk. If it is, then the kernel will load that page from the disk into the memory, into a fresh page frame, and then update the page table mapping and point to the fresh page frame. Similarly, if it is a page which is not yet mapped to a physical frame yet, so for example, under when this is what happens in demand paging, so you allocate more memory, the kernel gives you a new virtual page, but that page hasn't been mapped. So when a page fault happens, then the kernel gets executed, and now the kernel sees, okay, I allocated this page, but I haven't really allocated a physical frame. So in that case, the kernel will find a new physical frame that can be used, give it to the process, install it in its page table. After that, it re-executes the faulting instruction. So the next time the hardware does a page table walk, it is able to find a new page, new frame. So all those things happen when the present bit is not set. Another, the next thing or the next metadata is the read or write permission. So this essentially tells whether the page is writable or not. Uh, so if the write this bit is not set, so if it is unset,